Here, Marek Abramovich from Göteborg, who will talk about high-frequency oscillations of black hole accretion disks.
So the phenomenon that I am going to describe shortly today is certainly connected with radiative hydrodynamics of accretion disks. But we do not understand this phenomenon. And I will describe shortly our confusions and our frustrations, our theoretical attempts to understand the phenomenon. Let me mention a few people who are working together with me on the problem. The most distinguished one is Soji Kato, who was the first one seriously attempting to describe oscillations of accretion disks. But most of the people are students, some of them present in this room, like Eva Szramkowa from Silesian University and Odele Straub from Copernicus Center. So, first about the phenomenon itself. My first transparency is what we think phenomenon can be explained by. And we think that these high-frequency QPOs can be explained by a nonlinear resonance of some oscillatory modes in strong gravity accretion flows. And then the phenomenon itself. There are two complicated figures which I explain. First of all, these QPOs show themselves up in variability power spectra of some black hole and neutron star sources. Binary system in our galaxy, and also some people believe in accretion disks around supermassive black holes as well. So, X-ray variability power spectra shows several peaks, and for the binary system in our galaxy, typically there are two kinds of peaks. Low frequency peaks, which corresponds to few hertz variability, and high frequency peaks, which corresponds to a couple of hundred to a couple of thousand hertz. I will be mostly talking about these high frequency QPOs. So they come in pairs of two frequencies. And on this graph, on the left hand side, one frequency is plotted versus the other frequency. So the first thing to observe is that the ratios of these two frequencies in all microquasars that such pairs have been detected so far are sharply 3:2. So that is, to me and to some colleagues, very impressive, and it may be a sign of a resonance. In neutron stars, the data is here and different colors describe different sources. Situation is different, but also this 3:2 ratio can be seen, I claim, easily. Frequencies are varied along lines, I will display them later, and all these lines do cross this 3:2 reference line. Okay. If you make a histogram, number of points versus the ratio, the histogram peaks very sharply at 3:2. Now we claim that the fact that frequencies for neutron star sources are not fixed but they vary is a signature of a nonlinear resonance. that the resonance is not, that it is not only a resonance, but necessarily nonlinear resonance. And I will explain this later. Then, for 3 microquasars, masses have been measured by usual astronomical methods. These microquasars are in binaries, and we see the companions of observers in 3 cases measure masses. And then from these measurements we know that frequencies scale accurately like 1 over mass. You pick up, say, the upper frequency, and then for these 3 microquasars, and also for neutron stars, there is 1 over m scaling, which is a signature, which is easy to see, of strong gravity. Because a typical frequency in strong gravity would be velocity of light divided by gravitational radius, which of course gives you 1 over m scaling. Then there is another, and this phenomenology is known for some long time already. But there is something else, not very well known yet, because it was not yet properly published. It's a discovery by another young man in our team, Gabriel Perec from Silesian University, and Didier Barret from Toulouse. Namely that if for these 3 particular, but it also works for other sources, for these particular 3 neutron star sources, you plot amplitude difference. Of course, the observers do not only measure frequency of these oscillations, but also amplitudes. So you plot here the difference in amplitudes of 2 pairs versus ratio. And then you see that amplitudes and frequencies are correlated, like they would be in nonlinear resonance. And also that all these lines cross this point 322. So it looks like on one side of the resonance, one mode is stronger than another, and when the system goes through a resonance, there is energy exchange between modes. A phenomenon which we often see in nonlinear resonance. If you have a spring on a pendulum, then every one of you seen that we have either the pendulum mode or the spring mode at any given time. The energy is flowing from one mode to another one. And there is another important piece of observation coming from supporting the idea that that is the resonance between 2 modes, and it is what Ron Remillard is stressing, that most of the time we do see one mode, and that is particularly seen for this microquasar. It is not very well, so we see this mode here and that mode there. At a given time, we see one mode, and what is even more impressive is that it is really a mode that the behavior is purely sinusoidal. So it is not like we have a harmonics which gives this 3-to-2 ratio, but it looks like we have 2 pure modes. Additional observational evidence is that these QPOs have very high Q, very high quality factor of the order of 200 or more. You don't see this probably very well, but that is from the work of Didier Barret and collaborators, that the frequency itself is varied, but there are short duty cycles in which this oscillation is very coherent. So for many people, this means that it is unlikely that we do see something kinematical. Then another important piece of evidence, in several sources, but that is the best example, we observe pair of frequencies, and then after a very long time, because I forgot to say that these are transient phenomena. We do not see these QPOs all the time. We do see these QPOs at some times. So in this particular source, the pair of 300 and 450 Hertz pair of QPOs was observed by Strohmeyer in the outburst in 1996. And then the same frequencies, the same pair, have been observed 9 years later during another outburst. So now remember that frequencies, the typical time scales, orbital time scales, are hundreds or thousands of hertz, and we are talking here about 9 years. So that is a much longer time than any fundamental orbital thermal viscous time of the source. The fact that frequencies are repeated with exactly the same values means that there is a very accurate clock working here. And of course, perhaps the only accurate clock that is a black hole source, which comes to mind is orbital clock, that it must be connected. These QPOs frequencies must reflect orbital frequencies. Another interesting evidence from observations, which I'm discussing with Ed Spiegel, is that these low frequencies, these about 1 Hertz frequencies, and high frequencies, which are hundreds of thousands of times higher in frequency, are correlated. It is that you plot on one axis frequencies of these low QPOs, and on another axis frequencies of high QPO, one of the pairs, and then there is a correlation. The ratio is about 10 or 11, which goes from white dwarfs through neutron stars all the way to black holes. And again, one may say that it is unlikely that such a correlation could be explained by some, say, orbital motion of spots, for example. It must be a wave phenomenon. It is either that high-frequency waves are modulated and produce low frequency, or that low frequencies, e.g. connected to turbulence, excite high frequencies. We do not understand how it goes, but to many people that is a very strong indication that we do see something which is not connected to kinematics, but it is connected to oscillatory modes of the system. And then a direct proof that we may have resonances of modes. It is a millisecond pulsar. We do see frequency of the pulsar scheme and 2 high-frequency QPOs, and there is a sharp arithmetical relation between the 3 frequencies written here, which looks like the spin of the neutron star excites resonance in some oscillatory modes of accretion disk around this. then in my mind, and the same opinion is shared by a few of my colleagues, both in neutron stars and black hole sources, we have the same oscillations, the same modes, the same type of oscillations of accretion. But there are many differences between QPOs. I have no time to describe all the phenomenology, but our answer to that is that X-ray fluxes are modulated in a very different way in the case of neutron stars and black holes. And it is not something, I think, that we are adding ad hoc, but it reflects the fundamental difference between black holes and neutron stars. Namely, neutron stars have rigid surfaces and black holes have not. So we believe that oscillation, and that is, by the way, an old idea by Bogdan Paczynski, the great astrophysicist who died 2 weeks ago. So that is Paczynski's idea, how oscillations of accretion disks may modulate X-ray luminosity in neutron star sources. The thing is that when the disk oscillates, the accretion rate through the inner edge of accretion disk is very strongly modulated by an effect which was described in many papers and is very well understood. So it is this varying flux of mass which is hitting the surface of neutron star, and X-ray modulation occurs at the boundary layer of the neutron star. While in the black hole case, modulation is due to gravitational lengthening. The thing is that even if we see an accretion structure kind of etched on, which means not that the viewing angle is, say, 80 degrees or 60 degrees, then lengthening is strong. That is a simulation of what one would see if there is a ring of hot matter oscillating a little bit around black hole, and the modulation is sufficiently strong to explain what we see in black hole sources. So the differences we explain by this fundamental difference between neutron stars and black holes. Now, our mathematical model of these QPOs is more sophisticated than these few lines of arguments which I will show you. But really, at the end of the day, what we are saying is here. You have two coupled non-linear oscillators. Frequencies with which these oscillators oscillate are equal to their eigenfrequencies plus corrections that which depend on squares of both amplitudes. That is like if you would have one nonlinear oscillator, frequency is amplitude dependent. That is what I'm saying. But in addition, in systems in which energy of oscillation is constant, you have some quadratic form, and all these coefficients depend only on the oscillators. So they do not vary from event to event. They are given by the properties of the system. Then energy is conserved in this sense that the quadratic form of amplitude is constant, which means that amplitudes are anti-correlated. You can describe them by some parameter S. Okay, and you have anti-correlation of amplitudes, which means that frequencies are linearly correlated. That is the prediction of any weakly coupled nonlinear system of two oscillators. Whatever you have, that is one of the most general properties of oscillators. And for the prediction, from just this statement that we do have two weakly coupled nonlinear oscillators, is that there should be, in the lowest order, a linear correlation between the frequencies in that pair. Okay? And this is what we believe is observed, that there are linear feeds to many neutron star sources here. In addition to that, you do see that this bunch of lines is kind of crossing very near a particular point. That is also a prediction from this simple nonlinear pairs of oscillators. And we believe that this prediction is what we clearly see in the data. So that is not a success of the theory, because that's just a general property of any, I'm stressing this very strongly, of any weakly coupled nonlinear oscillators. But I would like to concentrate on problems which we have, on things which we do not understand. So I started with saying that the fact that frequencies are repeated so nicely from one QPO event to another indicates that these frequencies are connected to orbital frequencies. And one can think of many modes in accretion flows which are described by orbital frequencies. On this plot, we have here one frequencies. Because frequencies are scaled with mass, we can use also the mass here. So on this axis we have both mass and one particular frequency. Versus Kerr parameter describing the spin of the central black hole. And then there are different possible modes. This line, for example, describes two epicyclic modes being in the 3-to-2 resonance. Okay? Now, recently, several groups of, before I say this, and there are mass measurements here, here, and there, which I already mentioned, that masses are measured for three microquasars. But recently, few groups, and in particular the ones at Harvard, claim that from the spectral fitting, and that is radiative hydra, they may estimate accurately the spin of the black hole. So that would be, this box here would be mass estimate, spin estimate. And here, mass estimate, spin estimate, in two sources. Now the problem which you see is that there is no single line corresponding to a resonance of a pair of modes which would cross both this and that box. It may be that in different sources we do see different resonances, but that would be that is something which I do not like as a possibility. I would like to see some universal phenomenon here. Or the spin estimates are wrong. But let me repeat that this spin estimates are based on the state of art today of radiative hydro. This is the best thing humanity can provide. Right? So there is something wrong in some fundamental understanding of some important properties of accretion. Either in these oscillatory modes, which at the end of the day also depend on radiative hydro, but we are not doing that sophisticated analysis yet, or that spin estimates are wrong. And then I am very tempted, and I will tell this joke, or it means that Kerr geometry is wrong. When we started this QPO business, we often were saying that with QPOs, because it's a strong gravity phenomenon, we can test strong gravity. Okay? So a possibility is that these oscillations do not occur in Kerr geometry. And then what we do, in particular, research which is, I will describe this part which is somehow connected to radiative hydro. So this is what other people do. That is a simulation by Mami Mahida from Japan in a team, the same team as Roy Matsumoto and Kenny Nakamura work. And the interesting with respect to many respects, but in particular QPO's phenomenon, is that an inner torus is formed. Now this formation of this inner torus is a very delicate issue which is discussed among different teams of people who are simulating this. That is 3D MHD, okay, with radiative cooling. We are looking for oscillations of this inner torus. In the simulations, in the particular set of simulations Mami Mahida did, she was observing pairs of high-frequency QPOs which look very much like this observed, but it is not yet known whether this result is robust or not. So, following educated remarks of several of our colleagues, like Jean-Pierre Lasota, for example, we decided that we will also go analytic way, that we would like to understand what is going on in this numerical simulation analytically. And that is a figure from a paper by Omer Bless, Eva Shramkova, and a few other people, showing epicyclic oscillations of that calculated analytically of this tori, perhaps the same tori which Mami Mahida simulated in her simulation. And what is interesting, but that is a technical detail, and I will not go into technical detail a lot, is that in the limit, when the torus is slender, meaning that the cross-section to the arm of the torus goes to zero, these epicyclic oscillations are rigid. So all the velocity field is like all velocities are equal and parallel. But what we have done, and based mostly on calculations which Eva Shramkova did, is perturbative analysis of this torus, which is not infinitely slender, but we expand with respect to the thickness of the torus. So this torus has not zero cross-section. It has some small but finite cross-section. And the velocity pattern is different than just the rigid motion up and down, which may be important because when then we are interested in, as we should, in coupling coefficient between modes, in the limit of infinitesimally slender torus, all coupling coefficients for epicyclic modes are zero, and it is because they are proportional to gradients of or divergence of velocity field. When it is parallel and equal velocities, then of course it's zero, but in this case it may be not, and the hope is that we will find coupling between modes. And my last transparency is from an unpublished yet paper by Kluźniak and collaborators, which shows comparison between a few QPOs models, 3 QPOs models, which are mostly discussed. That is slope of the line in the frequency plane versus the ratio of frequencies. So for neutron star sources, because the ratio is, slopes are fixed, but ratio is varying, that is not an error. It is just that source is doing this. Okay? We may test on this plane predictions of 3 models. The first one is bit frequency model, which was proposed independently by several authors, and Lamp was the main supporter of it. Bit frequency model predicts that the slope should be 1. And one may say that this model is already rejected by the data. But there is another model by Luigi Stella and collaborators, which I will not describe, but it gives a very specific prediction of how the ratio should depend on the slope. In Stella models, this kind of behavior is not expected. Behavior should be, the changes should be along this region here. So that of course is a very biased argument by a supporter of a particular model, that you may look at it and you can pick up the favorite QPO model. Thank you very much. Thank you.
There's time for questions. Thank you, Professor.
Just a question concerning your observations.
Yes.
How are these observations observed? Are these optical or X-ray?
X-ray. X-ray. They are observed in X-rays, and they make standard Fourier analysis. So we construct power spectra. Some people start to do wavelet analysis as well, but that is only at the very preliminary stage.
Jürgen?
Yeah, I would like to understand more of the MHD aspect here.
Yes.
Because, as you said, it is very important to understand how much we believe this, let's say, care ideas they are finding. If I look in the star formation community in the accretion disk scenario, people do not understand that. That is because all the models we have for such an accretion disk are far from reality. There are people starting too fluid considerations now. It is not understood why the matter is transported inward. All these questions are not solved yet, so they are far. In your case, where you have such an accretion disk around the black hole or neutron star, how far are the current MHD simulations from reality in your view?
Well, I will answer your question. That's probably not the right public to say what I think I think that these simulations improved enormously in the last few years, and they are more and more sophisticated, and they are more and more realistic. But I think that they still are far from describing reality. And one of the examples of this is that in all accretion flows on compact objects, we do see these oscillations. They are not explained by numerical simulations yet. And because it is a very robust property of real accretion flows which exist in nature, which are not reproduced by this simulation, then that's an obvious answer that we do not understand in these simulations everything. But I do see other problem here, namely that also, first of all, I will say something which is an exaggeration, but I would like to say it anyhow. That, however sophisticated these simulations are, I do not see a single phenomenon of a single property which we learn from simulations and which was not before predicted by analytic methods. So that is, to me, these numerical simulations today illustrate beautifully and deeply some theoretical predictions, but it is not yet a science on its own safe, how to say, right? That it is not that numerical simulations are predicting new things. So that is my answer.
May I venture a comment about that? I should think that those colleagues who study non-axis symmetric perturbations in disks, such as spiral structure and things, would violently disagree with you, but I'll leave it to that community to take up this issue. Thank you very much again. Then our next speaker is waiting here in the wings already. There's Yuri Kotanen from Oulu, who will address us on super Eddington accretion winds and ultraluminous X-ray sources. Please.
I will discuss today also some aspects of radiation hydrodynamics, but I'm not going to discuss in detail the simulations that are involved in radiation hydrodynamics. I will show you some objects where this radiation hydrodynamics could be extremely important, and I will discuss ultraluminous X-ray sources. Those are bright X-ray sources that are observed in nearby galaxies, where radiation hydrodynamics and super Eddington accretion plays probably a very important role. So first I will start with a general introduction about ULX, so that everybody will understand what are those sources. I will talk about of the models of ULX that are proposed, and then I will talk a little bit about different models for super Eddington accretion that is probably happening in those sources, and I will concentrate on the recent paper that we did on super Eddington accretion with winds, and we hopefully come to conclusions. So what are ultraluminous X-ray sources? These are, as you see here, the antenna galaxy. In optical you have star-forming regions, and the same region in X-ray with Chandra you can see a lot of bright X-ray sources. So actually they were known already from the 80s, from the era of Einstein Observatory, but they were not known with such great details. Now we have very good spectra, and we have also time variability data for those sources. So most probably most of those sources that we see in or close to star-forming regions in those galaxies are accreting black holes. So the basic definition of those ultraluminous X-ray sources is that their bolometric luminosity should be larger than Eddington limit for about 20 solar mass black hole, few times 10 to 39 Earths per second, meaning because this is the theoretical limit, what should be the sort of upper limit on the mass of the black hole formed during the standard stellar evolution. if you maybe in population 3 stars can form even high mass black holes, but no, nowadays those black holes in normal metal-rich matter should not be more massive than that. So then those sources shouldn't be in the galactic nucleus, so we are not talking about AGNs, so because in almost every 10% of galaxies maybe, you have bright nucleus, sometimes those, or you have black holes, central black holes, and sometimes they're bright, so you see an AGN, sometimes they're not so bright. So we are not talking about AGNs here. And they shouldn't be resolved with the best resolution that you can get with camera, because there could be some sources like supernova remnants that could be also as bright as the sources that are like 10 to 40 arcs per second. So, why we think that these are accretion black holes? First, because they're variable, and this is one of the sort of nicest proof that this is a strongly variable source. A few years ago, Stromeyer and Makotsky discovered quasi-periodic oscillations in ULX and M82 with the frequency 0.06 Hz. And if you assume that these quasi-periodic oscillations are coming from the sort of Keplerian motions in the innermost part of the accretion disk, you come to the conclusion that the mass of this central object should be a few times or 20,000 solar masses. But the problem here is that many galactic black holes in our galaxy, in the Milky Way, which we are sure that they don't have such huge masses, like Cygnus X1 and GRS 915, and there are many other sources. They show very similar features, quasi-periodic oscillations, and very similar frequencies. So this is not a very good argument. But we still believe that these frequencies are somehow associated with the accretion disk, and just the problem is that these are very low frequency oscillations. These are probably not Keplerian, because these are not Keplerian motions, but these are some global oscillations of the accretion disk. Maybe some convective motions, as we will talk later. So, do we have ULXs in our galaxy? And this is an example of what I would call transient ULX in our galaxy. V4641 Sagittarius. This is a black hole, a accretion black hole, and it was bright for, so it was rather bright 12 Krabs. Here you see new spectrum. If you integrate from optical to X-rays, and you assume the spectrum which is flat, and you'll get luminosity 10 to 40 Hz per second. So this is clearly not far from what we see in ultraluminous X-ray sources in other galaxies. There is another example of such a bright source in our galaxy, which is SS433. We don't really know what is the total luminosity of this source. There are just indirect evidences that this source is very bright in the UV range, and there was an estimate by Dolan et al. 97 that it's about 10 to 40 also Hz a second. But this source we do not observe sort of face on. It's hidden by the wind, probably from the accretion disk, and this wind makes a deep nebula around the source, and these kind of nebulas we also observe around ULXs in other galaxies. So there is some...
Sorry to interrupt you, but to be fair, with SS433 it's a spin, it's processing beam, it's not just the wind.
Yes, so this is produced by the jet, this nebula is probably produced by the wind. Because the jet processes about 20 degrees around, so this feature that's a jet, yes. But if in other galaxies you see sort of nebulas around the ultraluminous X-ray sources too, and if you see a face on this nebula, you will see probably a rough circular diffraction. Okay, so there is some similarity here. Of course, it's difficult to argue that ULXs are like SS43, but there are, as we will see later, there are clearly a lot of similarities. So if you look at normal galactic black hole candidates in another galaxy, they all show very standard behavior if you plot luminosity versus the temperature. If you measure temperature from the theta of the X-ray data, they all show very nice correlation. Luminosity goes temperature into power 4 with very small deviations. And the difference, of course, between different sources here could be related to the fact that we don't know exactly the distance, so we don't know exactly the luminosity, and also they can have different black hole spins. There is one nice exception, or very interesting exception, in Large Magellanic Cloud. There is source X and CX1, which doesn't show this correlation, which just shows exactly perpendicular to that. Because this correlation is from the standard accretion theory. You just have fixed size, you increase the luminosity, temperature goes like luminosity in power 1/4. Okay, so LMC X1 doesn't behave so nicely as those other sources do. If you look at the ULXs, so here we are now in the Milky Way, ULXs show some soft spectra, not all of them, but many of them. If you think that these soft components that you see at temperature of the order of 0.1, 0.2 kiloelectron volts, if you think that these are produced by standard accretion disk, you have to take this correlation, put it over there, in order to go through those points, and therefore you have to increase the mass from a few solar masses to a couple of thousand to a few 10,000 solar masses. So, is this an explanation then that these sources are intermediate mass black holes? Not necessarily. First, there are many of those ULXs show also some hot spectra. So here you have examples written in the ASCA observations, where you see temperatures of order of 1 to 2 kiloelectron volts. So there is clearly some discrepancy. We have soft components of 2 keV, we have hot components up to a few keV. So what's wrong? Do we have any other clues about the behavior of ULXs? Yes, we do. Franklin Carr, just in a recently posted PH paper, plots luminosity temperature correlation for one of the sources, 1313, and it doesn't follow at all standard accretion disk behavior. If you plot those, this is the same source, it varies in time, and it shows negative correlation between luminosity and temperature. It's just this would, what the standard accretion disk would do, this is what you see. Something is clearly wrong with our interpretation of the standard accretion disk. Okay, so what are the models for ULXs? I would mention that it could be super Eddington accretion. There are a number of versions of that. I mentioned a few of them. Mitch will probably mention during his talk about photon bubbles. I'm sure Ari Socrates will also mention this. So where you really achieve super Eddington accretion isotropically, so for any observer it will be, you could see very large luminosity. You can have other possibilities if you dissipate energy in the corona, not in the where you have most of the disk. The standard objective disk, swing disk model also could be applied because if you have very high accretion rate, you could achieve luminosities of the order of 10 times Eddington. But all this when at such high luminosities also you can form winds, and I would argue then that the super Eddington accretion with winds probably is the most natural explanation for the behavior of the ULXs that we see. There was also other models. For example, you can have a standard stellar mass black hole accretion at sub-Eddington rate, but you somehow beam this radiation in, you can do it in the jet, or if you make some beaming by accretion disk, which is not clear how you do it. But basically, then you would beam all the radiation in one small solid angle. The problem with this interpretation is that you see those nebulas, and you can estimate the luminosity of the ionizing source from the nebulous, and it's clearly quite high. So this beaming doesn't work really. And then of course we have this intermediate mass black hole interpretation where you have 10,000 solar mass black hole accretion at sub-Eddington rate. And here it's not clear why those black holes should produce outflows that you see at all. So now I will concentrate on super Eddington accretion disks. So there are two versions. One is conservative accretion disk, or there are a couple of versions of that. All the papers which people call college donuts, or slim disks, where one assumes that the accretion disk, the accretion rate is constant, so all the mass is accreted to the black hole. There are other versions of super accretion disk where you assume that most of the mass, or a large fraction of the mass, is blown away by the wind. Actually, this was already proposed in the seminal paper by Shakur and Sunayev at 73. And there were a number of papers discussing applications of this model. Of course, most of these papers were written much before we even knew about ULXs. But we can apply, of course, the same theory nowadays when we to the data that we have. And there were a number of radiation hydrodynamic simulations, and I will show you results from the recent paper by Asuda. So, superradiant accretion with the winds. This is what Shakur and Sunet wrote in their paper, that if you have very high accretion rate, much above Eddington, much of the mass can be blown away, and in order to have a stable solution, and I will explain you why, the accretion rate as a function of radius should drop linearly. So this is the initial accretion rate, and there is one can introduce a so-called sterilization radius, where the disk starts to feel that it is super Eddington. It means that at some point in the disk, you have basically a radiation force from the disk will exceed the gravity force, the vertical component of the gravity force. So and then, so what you can say that if I have the energy dissipation per unit area, which goes to about gm m dot accretion rate over r cubed, so it should be balanced by should be proportional to the vertical component of gravity, and if h over r, the height of the disk, is of the order of unity, then you would get from this simple relation that mass accretion rate should go linearly with radius. Then automatically you get that the dissipation rate or the radiation that you can that can escape from unit area should go like 1 over r squared, and you get in that situation that the spectrum that we observe should go like frequency to power minus 1. So nu if nu it should be a flat spectrum, what we see, for example, in this transient ULX in our galaxy, where 46, 41 is Sagittarius. If you integrate the spectrum, or if you integrate the dissipation of a radius, you get that the total luminosity of the disk is about Eddington times some logarithmic factor, which could be of the order of 10. So you easily get 10 Eddington luminosities, and if you beam this radiation in the wind, then you can get even factor a few more. Okay, now I will show you some figures from this radiation hydrodynamic simulation by Asuda, and later we'll try to understand how this simulation, or how we can understand those simulations. Okay, so what they did, they put some light mass accretion rate more than 1,000 Eddington. Actually, I think one should divide this by 10. So I think 10 here, it corresponds to the Eddington luminosity. Okay, but this is the accretion rate into the black hole. So this is the total mass here. So, but anyway, so the accretion rate, they managed to get in the simulations a more or less stable solution, steady state solution, quite steady state. So they're capable of running the simulations for sufficiently long time. And so we have inner flow in the equatorial plane somewhere, and then there is most of the gases flowing out in the cone around the rotational axis. And there are some convective motions in the rest of the accretion disk. So what's interesting that if you plot accretion rate as a function of radius, this is logarithmic scale here, it goes linearly with radius, which is very similar to what Shakur and Snap already proposed a long time ago. The only difference is that the mass that goes into the black hole is still above Eddington. So in Shakur and Snap, in their approach, the mass that goes into the black hole is very close to Eddington. And the difference is that in this situation, you have advection, so it means that not the efficiency of accretion of the radiation, of course, is not 100%. Most of the energy is advected to the black hole. Therefore, you still can have larger accretion rate into the black hole than Eddington. Okay, if we have those simulations, can we understand some simple model what they mean? A few years ago, Galina Liponova had sort of developed a simple analytical model of the supercritical accretion with outflows, where she assumed that she added in the momentum conservation term a term which is responsible for loss of the angular momentum by the outflow of matter, and then she assumed that the mass that is outflowing, so the m dot of the r, is a fraction of the available energy that we have that comes from radiation. So, and actually in first conditions, in her discussion, she assumed that this fraction epsilon is 1. So basically all the energy that we have in radiation is taken away by the mass, by the outflowing gas. Of course, in that situation, there is no radiation left. So no energy left for radiation, everything goes into the outflow. And of course, in reality, what is epsilon is not clear, how much energy you can put into the outflow. But if it's half, then half of the energy can escape as radiation, half of the energy can escape in the form of the kinetic energy outflow. Okay, so if you assume that epsilon is 1, and you assume that there is no any advection, then one can solve these equations, and one can get an analytical solution of how the accretion rate goes with the radius and how the dissipation rate goes with the radius. And because here, dissipation rate and radiation flux sort of is the same thing. So the accretion rate goes with the radius almost exactly as was discussed by Shakur and Sinet in 73. So here is sort of self-consistent solution of those questions, but you can get the same thing sort of just on the very simple analytical argument. Now, if we put in advection, we now in the recent paper discussed that model, the situation, of course, changes because now you can have more gas which is accreted in the black hole. So here on this plot, there is accretion rate in units of the starting accretion rate that we have, and here is the radius. So our analytical model will give you this behavior. So I make this is linear scale here and logarithm here. So actually this curve is linear. Mass goes linear with radius. Don't be surprised by such strange shape. But if you include, so here, of course, the accretion rate is very small. It's not 0, it's 1. But the units are, you put accretion rate 1000, so it's here very small. Okay. But if you include advection, then the mass accretion rate will depend on the amount of how much energy you put in the outflow. If you have pure advection, there's no outflows, of course, mass accretion rate is constant. If you put all the energy in the outflow, then of course half of the mass about can escape, but in some intermediate cases you can maybe have 30% of the mass that will be escaped into infinity, and 70% of the gas which will be accreted into the black hole. What's interesting is that all these models predict that the radiative efficiency, sort of the radiation flux as a function of radius, is almost identical in all these models, independently of what we put in. So analytical model, what I plot here is radiation flux times radius squared. So because we expect in those disks that radiation flux goes like r to minus 2, therefore if I multiply by r squared, I will expect flat behavior, and this is what I get in analytical solutions. And so this flat behavior goes from very small radius up to this polarization radius where the disk field that is supercritical, where the outflow starts. All these adaptive disks predict very similar behavior. This is high mass accretion rate. You have also basically flat dependence, and then it goes to at some point it goes to the standard disk where this radiation flux goes like r to minus 3. So I also should point out that this mass accretion rate as a function of radius can be described by linear derivation. Sort of a nice, this is just a fit sort of to the simulations. So from here, now we can try to understand what should be the properties, what should be the radiation that you should see. Because if first the outflows that we have should somehow affect the spectrum of radiation. We can plot the optical depth for the outflow as a function of radius in two different directions. One is perpendicular. This is perpendicular to the disk, sort of for the face-on view, and one to the parallel to the disk, because it's much larger, you cannot see through the. So the maximum optical depth goes like square root of the accretion rate. What's interesting is that if you estimated time diffusion time of photons through this disk is about the same as dynamical time scale. So it means that the photons that are originated at some radius, let's say 10 times the inner radius of the disk, they will escape at the radius of the order of 2 times, like that. So in reality, if you have a power law spectrum that is produced by underlying accretion disk somewhere here, this outflow will affect it slightly. It will shift it to the software energies, but the power law will stay a power law. So it will not change very dramatically. Of course, for the age-on observer, what I would like to point you out that this is called the photospheric radius is here. So if you look at the accretion disk age-on, you will find the photosphere. This is computed assuming you have Thomson capacities only. You will see photosphere which is at very large distances. This is distance in units of inner accretion radius. So this is the tenth of thousands of gravitational radius. Extremely large. So therefore you will not be able to see the central source at all. You will see only very soft radiation from the photosphere. If you look from the top, then of course you will see all the energy that will be dissipated in the inner part of the disk. And this part of the accretion disk will give you the flat spectrum that looks just like that. This is new spectrum. So inner part of the disk will give you some maximum temperature, and the part where you have this, where the outflow starts, the sterilization radius, you have the break in the spectrum. And then it will go to the standard accretion disk. So this model predicts that in you have flat spectrum, and we can estimate what are the temperatures of those 2 peaks, or one can think that these are 2 peaks in the data, in the model. So the maximum temperature and the temperature sterilization radius. They are functions of the accretion rate. One is actually depends very little on the accretion rate, and the sterilization radius will depend on the accretion rate as inverse square root. The photosphere, also we can estimate the temperature of the photosphere, I didn't plot it here, which goes as mass accretion rate in the 3/4. Now, if we estimate, if you put now those temperatures on the diagram, the luminosity temperature diagram for ultraluminous X-ray sources, this is what we see. So I will take, for example, 15 solar mass black hole. This is what the maximum temperature is. Of course, somewhere here at low luminosity is the standard accretion disk. At high luminosity, the maximum temperature is constant. Then the sterilization temperature is decreasing as the luminosity is increasing. And the photospheric rate temperature is really decreasing more because it goes like a stronger function of the accretion rate. So some points here, these are ULXs that we see, fitted with 2 black bodies. So you take black bodies, you fit with 2 black bodies, and so what we see that some of the points can be described, for each source has 2 points here. High temperature can be described by this high temperature component, and low temperature can be described by this temperature sterilization rate. There are 2 sources, for example, this famous SS433 that shows very soft emission, so with the temperature of the order 30 or 50,000 Kelvin, and if you put luminosities of the order 10 to 40 hours per second, it will be here. So this is consistent with the accretion about 1,000 Eddington onto the 10 solar mass black or 15 solar mass black hole. Okay. What's interesting also is that this is LMCX1. Probably you remember in the beginning of my talk that LMCX1 has showed completely wrong correlation of luminosity versus temperature. This is the black hole in large Magellan cloud. But in this diagram, if I multiply its luminosity by a factor of 5, it will end up here. So it seems that this source is also an ultraluminous X-ray source in our galaxy. Because it shows this anti-correlation. Of course, on this diagram, it's very difficult to see that it's anti-correlated because the luminosity here is sort of, I spread this viewer. But it shows correlation similar to how the sterilization temperature would behave as a function, as a function of luminosity. So, conclusion is that it seems that supernatant accretion on the stellar mass on any black hole of course, should produce winds. The observed luminosity is much larger than Eddington because of the first logarithmic factor, and the second because of the beaming in the accretion disk. And ULXs are consistent with the super-radiant accretion onto the 10-20 solar mass black holes. You need to have winds because you see nebulas around those sources. And ULXs are probably similar to what we see. So we have a couple of ULXs now, Galaxy SS433 and LMC-X1. And in reality, there could be similar ULXs containing neutron stars. And Circinus X1 is the prime candidate because sometimes it shows 10 times Eddington luminosity. So I would also guess that it would be good to look for ULX features in those sources. And I'll stop here. Thank you.
Thank you. Yes, please.
Sorry, I know you said it, but I think I missed it. So you corrected the luminosity of the LM6
Yes, what I did here, I multiplied the luminosity by a factor of 5. Because what is plotted on this graph is bolometric sort of luminosity.
Or isotropic luminosity, so because of beaming? Or
No, what I plot here, when I plot theoretical models, is bolometric, total, integrated over angles. And of course, what we see in LMC-X1, who knows? If you look at this age on, you see maybe only 10% of what sort of.
Right, so it's an isotropic for
Yes,
right.
yes. So I corrected this luminosity by factor 5, and it sort of fits to this diagram.
But the factor is arbitrary.
Yes, of course. I just put it by hand. Because then it shows correlations what you expect from this theoretical model.
First Marek and then Harold.
Very short. In conclusion to your growth, super Eddington accretion produces strong queens. What does magic produce?
Okay. First, of course, there are.
You repeat the question.
Mark said that I wrote that super Eddington accretion produces winds, and he would be more cautious, and he would say that it may produce winds. So it's not a comment. It's just a comment. I think, of course, Mark, of course, is right. Yeah. But we see evidences that super Eddington accretion produces winds, both observationally and there are also numerical simulations that seem to support this view.
Harold, and then Paul, last question.
Okay. I'm curious about this ignorant question about the properties of ULX in terms of what kind of galaxies they can be found in. Are they mostly in star-burst galaxies? Is that shows
They are in star-forming galaxies, yes, because I guess that most of the ULXs, the number of the ULXs, if they are formed in the you need a black hole and a massive companion next to it, because that's the only way you can get a very high accretion rate.
would they then
So-
dominate the X-ray flux of this entire galaxy?
It's certainly an antenna. They are much. There is no AGN there, so it's.
The answer is the definition of ULX is any extragalactic point X-ray source with a luminosity greater than 10 30. Now that's the definition. And that definition is put by IBM the use case. If that's the definition, then they're found in all galaxies, all of the galaxies. However, the ones that we're talking about, the ones that are 10 to 4 years per second, which is 10 times the luminosity per 10 solar mass black hole, are only found in stars.
I guess.
Sorry, I have to.
Okay.
Sorry, thank you for calling. Paul, last question.
Is there a connection between the ultraviolet X-ray sources and SS433 that they were common,
Yes.
like SS433? Is there any connection between the ultraviolet X-ray sources and the production of the relativistic jet? There are models that include my own from years ago in which radiative acceleration produced the bullets that were moving at 0.26 times the speed of light, and they required super Eddington luminosities if it was result from hydrogen resonance scattering. It didn't require super Eddington luminosities. It started at the surface of a neutron star with something like iron atoms. I'm just curious, is there any connection then between your production of the winds and the production of relativistic outflow?
Yeah, we don't discuss the production of relativistic outflow, and in SS433 we have the jets, and in ULXs we have no clue whether they have jets or not. I mean, so it's difficult.
All right, I suggest we thank our
Yes.
speaker again. I'm going to invite the final speaker of this morning, Ms. Omer Blaise from the University of California, Santa Barbara, on the title you see announced here.
Well, after yesterday's really incredible simulations of stellar convection, I'm almost embarrassed to come up here and tell you about the state-of-the-art of accretionist simulations. But hopefully, maybe after my talk, I'll actually convince many of you who are working on stellar convection to transport some of that impressive hardware to this problem. We still don't understand very zeroth-order basic questions about the structure of accretion disks. You all know, for example, that the sun is powered by nuclear fusion reactions in its core, that heat is transported outward by radiative diffusion in the deep interior and then by convection further out, and that the sun is supported hydrostatically against its own gravitational field by gas pressure gradients. We don't know the answer to any of those questions when it comes to the vertical structure of an accretion disk. That's how ignorant we are. Accretion power is liberated by turbulence. We do not know the optical depth distribution of that dissipation. We don't know how heat is transported through that turbulence. And we also don't even know what is supporting the vertical structure of the disk against the tidal gravitational field of the central object, whether it be gas pressure gradients, radiation pressure gradients, or magnetic fields. The simulations that I'm going to show you today, hopefully answer some of those, provide preliminary answers to some of those basic questions. But as I say, it's somewhat preliminary. Let me mention my collaborators here. The work that I'm going to be showing you is done in collaboration with Julian Krolik and Shigenobu Hirose. Shigenobu Hirose is the numericist in this collaboration. He is the one who actually worked on improving Zeus 3D with flux-limited diffusion, which was originally developed by Jim Stone and Neil Turner. Julian Krolik and I are merely the data analysts in this collaboration. So this guy did all the simulations, and we've just been taking the data from the simulations and trying to figure out what it means. The papers that are describing these recent simulations just came out last week on AstroPH. So if you want to understand how accretion disks work, you need to understand how angular momentum transport occurs in accretion disks, and that is widely believed, at least in highly electrically conducting disks, such as those that are in orbit around black holes and neutron stars, to be due to the magnetorotational instability. So a very quick tutorial on how the MRI works. If you imagine, at least in its simplest version, if you imagine two rings of fluid in orbit around a central rotation axis that are threaded by a magnetic field, and I perturb this ring inwards and I perturb this ring outwards, then your immediate reaction would be that the magnetic tension that is then created in that perturbation will snap those rings back into place. But there's another effect here in that when I perturb this ring inwards, it initially conserves its angular momentum, so it's spinning faster. This ring is spinning more slowly, and so the magnetic field actually has an azimuthal component pointing into the board here. That azimuthal component torques down this inner ring, costing it angular momentum, and therefore its centrifugal support decreases, and that actually causes it to fly further inward. This ring, on the other hand, is being torqued up. It gains angular momentum. It increases its centrifugal support, and so it flies outward, and that can drive an instability. This azimuthal torquing wins over magnetic tension if you can wrap the field line around for a full orbit before an Alfvén wave can actually communicate magnetic tension forces between these two rings. And so that translates to a criterion where the Alfvén speed divided by the angular velocity must be less than the wavelength scale of this instability. So if you have a weak magnetic field or long enough length scales, you will drive the disk unstable. And when you simulate the nonlinear development of this instability, you generate fully three-dimensional MHD turbulence, which transports angular momentum outwards through a stress which is related to velocity correlations and magnetic field correlations, that is a Reynolds and Maxwell stress that transports angular momentum outwards. And this is what is now thought to be producing the anomalous angular momentum transport in accretion disks. There have been many, many simulations of the MRI in accretion flows. Perhaps the most impressive are global general relativistic MHD simulations of this in a Kerr space-time. John Hawley, for example, has done these simulations, and you see these wonderful structures here, and we're getting perhaps a basic idea of what the global flow looks like around a black hole. But there's a very serious problem with all of these simulations, and that is that it doesn't include photons, it doesn't include heating, and it doesn't include cooling. In other words, there's no consistent thermodynamics in these simulations. So pressure forces are not, you can't talk about them really, you can't talk about what this disk looks like, and one of the most serious issues for black hole accretion, at least in the case of quasars and X-ray binaries, is that in the innermost parts, the Shapiro-Semyayev models that we've been working with for 30 years now are predicted to be dominated by radiation pressure. And again, for 30 years, it's been thought that those inner radiation pressure-dominated regions might be thermally unstable. If you take a Shapiro-Semyayev alpha stress model where the stress is proportional to the total pressure, you expect those radiation pressure-dominated regions to be unstable. And you cannot address those with simulations that don't have photons, that don't have radiation pressure. The reason why that thermal instability exists is that the dissipation is proportional to the square of the radiation energy density, while cooling is proportional to the single power of radiation energy density, because these inner regions are electron scattering dominated, and because you have a higher temperature sensitivity on the heating rate than the cooling rate, you have a thermal runaway. But this is purely due to this assumed prescription. People have invented other prescriptions that might hold here, and those are thermally stable, and we have no idea what's going on. Without knowing how MRI turbulence behaves in the presence of radiation, we don't know what's going on here. And these are the innermost, most luminous parts of accretion disk, the power quasars and X-ray binaries. So this is a fundamental question that we've been living with for over 30 years. Some understanding of how MRI works with photons has been obtained with local, non-stratified shearing box simulations. These are simulations that I'm showing you by Neil Turner, who was here, Jim Stone, and Takayoshi Sano from a few years ago. Although MRI turbulence is subsonic with respect to the total sound speed determined by both radiation and gas pressure, it turns out, under conditions that you expect in the innermost parts of accretion disk, the photon diffusion time is actually quite rapid. So on the time scale that the MRI attempts to squeeze the gas, photon pressure would normally cause an incompressible response, but photons are diffusing out of that squeezing parcel of gas, which causes an enormous increase in compressibility. And so under the conditions you expect for MRI, you actually have highly compressible turbulence. The ranges of densities that are shown here range by a factor of 10 in this turbulence. This is highly, highly compressible. You also expect strong density fluctuations from something called the photon bubble instability. This is not Ed Spiegel's photon bubble instability. This is a terrible name for this instability. This is actually a radiatively amplified magnetosonic wave, and as Mitch Spiegelman has shown, this radiatively amplified magnetosonic wave turns into a train of shocks, at least initially. And that produces paths over which photons can diffuse outward quite rapidly, possibly allowing super Eddington luminosities without driving an outflow, and also strongly altering the spectrum that you would expect from the surface of an accretion disk. Neil Turner is going to explain the physics of this in much more detail later on in his talk this afternoon. So what we're doing here, we cannot do a global radiation MHD simulation of an accretion disk around a black hole. So we're doing something much more modest. We're considering a little box inserted into the disk. This box co-rotates with the fluid, so you're in a rotating reference frame. The boundary conditions are that it's periodic in the azimuthal direction, it's shearing periodic in the radial direction. That is, the walls of the box themselves are what are enforcing differential rotation within the box, and you have outflow boundary conditions in the vertical direction, of course. The particular simulation that I'm going to spend most of this time talking about is a modest resolution simulation. It has only 32 zones in the radial direction, 64 zones in the azimuthal direction, and 512 zones in the vertical direction, because we are really interested in getting at the vertical structure here. The zone size in each of these directions is the same, except for the azimuthal direction, where the zone size is actually twice that in the radial and vertical directions. So you're well resolved that I'm talking about a very skinny radial box. It's very, the shearing walls are very close to each other in this box. And it's very, very extended in height. Yes, go ahead.
Aspiration cells or?
I'm sorry,
The cells are unit aspiration?
the cells are, no, because in the azimuthal direction, the cell size is twice as long as in the radial and the vertical directions. The radial and vertical directions are the same. Someone asked for equations. There are the equations. Radiation MHD. The reason why I'm putting them up here is just to point out that they're in the gas momentum equation. We have to impose a Coriolis force, a force which balances a net force from gravity and centrifugal forces, and then there's the tidal gravitational field from the central black hole, which increases linearly with height here because it's a tidal gravitational field. The gas and radiation internal energy equations are solved separately, and there's the code also solves a total energy equation, so that When magnetic fields annihilate at the grid scale, for example, that energy is then captured and put into heat in the gas. And the energy conservation in this code is extremely is very good. Here's the thing that you're all going to criticize. We're using flux-limited diffusion. There's the flux limiter. It's a standard Livermore-Pomeranian flux limiter. I'm not going to defend it here. Please, if you want to do something better, I welcome you to do this problem. And actually, this is almost virgin territory. There have only been 3 simulations of these vertically stratified disks done at all. The original one was a pioneering simulation done by Neil Turner a few years ago. He used the code that existed at that time to actually explore the radiation pressure dominated limit, and he got some extremely interesting results. It was expected for a long time that convection would be an important source of energy transport in those regions, but in fact he showed that the structure that developed was convectively stable, and that radiative diffusion was the main source of heat transport. He also found no evidence of a thermal instability, although he would agree with me that that result is preliminary, I think. The code has been improved since Neil did this by Shigenabu Hirose. It conserves energy better. It's parallelized. It can access low enough densities that we can actually insert the photosphere inside the simulation. And Shigenabu Hirose published a simulation which was gas pressure dominated. And the simulation that I want to talk to you about today is one where the radiation pressure is comparable to gas pressure at the midpoint. So we're working our way back up to the original regime which Neil explored. So here's a slice through the disk. The colors show density. This is a constant radial slice through the middle of the box. The black arrows show magnetic field lines. You can hardly see this, but there are dashed lines here which show the position of the Roslin mean, that is electron scattering, really photosphere here. This is at 90 orbits, 150 orbits, 300 orbits into the simulation. You can see that sometimes the disk is hot, sometimes it's cool, sometimes it's hot. And there's lots of interesting structure here. If I plot the total energy content in the box as a function of time, the dotted line here shows the gas internal energy, the solid line shows the radiation internal energy. Of course, because radiation goes as T to the 4th, gas goes as T. The radiation, when you heat and cool the box, the radiation and energy responds much more greatly. The dashed line here shows the magnetic field energy multiplied by a factor of 10. The actual magnetic energy in the box is less than the gas internal energy at all times in this particular simulation. But we blot it up by a factor of 10 because it's rather interesting. You can see that it's fluctuating and that these fluctuations are correlated with the fluctuations that you see in the radiation, with a lead. And that's simply because the turbulence is getting stronger, most of the energy is in the magnetic field, and it dissipates, and then that dissipation appears a little bit later on in the radiation energy content, and then it's radiated away through the photospheres. 300 orbits corresponds to 40 cooling times, 40 Kelvin times if you like, so there's plenty of time here to reach thermodynamic equilibrium, thermal equilibrium as well as dynamic equilibrium. If you plot the volume integrated dissipation rate at every single time as a function of the total energy content of the box, you get this horrible mess here. I should point out that most of this dissipation is due to numerical resistivity. Basically, it is that annihilation of magnetic field lines at the grid scale, which we then turn into heat. It is numerical, it's artificial. Actually, let me point something out. I forgot to point something out here. Here and here, when the disk was hottest, you cross the nominal Shakura and Sunyaev thermal instability boundaries. So if the stress was proportional to the total pressure, the disk should have gone thermally unstable here and here, but it did not. And this lasted for about 4 or 5 cooling times in each case. The reason for this, I think, is what we see here. This is a scatter plot, but this is a line that shows dissipation rate proportional to total energy, and you can see that overall, average, the dissipation rate is roughly proportional to the total energy, not proportional to the total energy squared in this regime. It turns out that the cooling rate is also proportional to the total energy because, again, we are electron scattering dominated. So the heating rate, if you like, is proportional to the same power of temperature as the cooling rate. So this is a marginally stable configuration that we're talking about here. And that's why we see probably strong fluctuations in the energy content of the box. It's marginally stable. At times of high energy content, though, you might convince yourself, although it's not completely clear, that this is turning over and flattening a little bit. Maybe. if the dissipation rate is going as a power of energy less than unity, while the cooling rate still goes as that power of energy to the first power, then the dissipation rate has a weaker temperature dependence than the cooling rate, and you end up with stability. So it appears at times of high energy content that you are actually thermally stable. We do not know if this will extend into the radiation pressure dominated regime. You can look at the spatial distribution of this dissipation rate as a function of column density, or optical depth, really, again, because we're scattering dominated here. So these are the surface layers. This is the deep in midplane, and so we're talking about optical depths of between 10 to the 4 and 10 to the 5. And the dissipation rate basically scales as the column density to the -1/2. Now, that means that they're, at least per unit mass. So, locally, the greatest dissipation per unit mass is occurring above the photosphere of this disk. But that's not a UFmu plot. If I multiply that by mass, actually, the volume integrated dissipation is peaking at the midplane. So this is like the sun. Most of the heat generation is happening in the core, in the midplane, not near the surface. That's a key point here.
Is that not
Yes.
related to your artificial dissipation of the magnetic field?
It may be. So most of the dissipation is occurring in the MRI, we're going to find out later when we look more at the structure, is in the MRI turbulent regions. And that's where most of the field annihilation is occurring at the grid scale. Whether that's real or not is unclear. So the argument is that most of the dissipation is happening actually in 1/1000th of the zones at any particular time where the field gradients are extremely strong. So if turbulence is cascading down to smaller length scales, and if that grid scale, if we're just capturing that heat, then we're accurately modeling that dissipation. But whether that's true requires real resolution studies, and we've not done that yet. That heat, which is generated mainly at the midplane, is transported outwards, and so this is the outward energy flux as a function of height in the disk, and the red curve shows the contribution to the photon radiative diffusion. And that completely dominates. This is a log scale, so heat is generated at the midplane, and it's transported outward just by radiative diffusion. The blue curve shows the contribution due to pointing flux. The dashed curve shows advection of radiation internal energy. And I apologize for this, but there's a green curve down here that you probably can't see, which is advection of gas internal energy. So radiation diffusion dominates the heat transport here. If we zoom into the photospheric regions, this is, again, a slice through the middle of the box at the highest energy epoch. This dashed line shows the Rossland main or scattering photosphere. This dashed line shows the effective photosphere where the spectrum would actually form. Both of these defined by the horizontally average structure. You can see that there's a lot of interesting structure. The colors show density, the red arrows show velocity, and the black arrows show magnetic field. There are very, very strong density fluctuations up here, both in the photosphere and the thermalization photosphere. I'll tell you why in a second, but I want to point out some obvious structures here. There's a shock here, and a shock here, which is very reminiscent of what a photon bubble shock train might look like. But we don't think that these are photon bubbles. As Neil will hopefully explain in his talk later when he discusses the physics of photon bubbles, this radiative amplification of magnetosonic waves occurs because of a correlation between radiation flux, radiation pressure, and velocities in the wave. And the expected, this just shows where that correlation occurs at a particular height. On this side of the graph, that's photon bubble-like. On this side of the graph, this is anti-photon bubble, so you shouldn't have any radiative driving at all. And near the photosphere, at high heights, in the annulus, you are biased towards this side of the graph.
Anti
We are not
means dense?
Go ahead.
No, you said anti means...
Yes, so...
What does that mean, dense?
So it means that the radiation flux is going against the fluid velocities. You're not driving it, you're damping it. And so, because it's biased in this direction, we don't see the expected correlation that we would have expected from photon bubbles. So we don't see evidence for photon bubbles in this particular simulation, which, remember, however, is not radiation pressure dominated. How much time do I have? I said I've talked to Kathy. If we look at the dynamical support against gravity, what's actually supporting the disk vertically against the tidal gravitational field of the central black hole, that's shown here, again at the high energy epoch. This solid line is the actual total gravitational acceleration. It varies linearly with height because it's the tidal field. The contributions to vertical support due to gas pressure, that's green, radiation pressure, that's red, and magnetic forces are blue up here. And the total is this dashed solid line. So you can see that hydrostatic equilibrium is very good in the middle regions. There are fluctuations about hydrostatic equilibrium in the surface layers, but it's more or less at the right value to more or less balance the disk against gravity. And those, the forces out here in the photospheric regions are due to magnetic field. They're not due to radiation pressure, they're not due to gas pressure. The surface layers of these disks are dominated by magnetic fields. And for those of you who are stellar astronomers, you're not going to be surprised by this, but realize that the magnetic support extends deeper than the scattering photosphere and deeper than the thermalization photosphere here. So magnetic fields are much, much more important here in a disk than they are in a star. In fact, they're even stronger than you would have expected from that, because if I decompose these magnetic forces into magnetic pressure gradients and magnetic tension terms, the magnetic pressure is cyan here, the magnetic tension is magenta, and the total is this blue curve again. You can see that we have strong upward magnetic pressure gradients and strong downward tension forces, and they nearly cancel each other out to produce the total magnetic support against the tidal gravitational field. This is a volume average of these forces. If I do a mass-weighted average, which perhaps looks more at how the thing is actually supported, these downward tension forces are reduced by about a factor of 2. So it's still magnetic pressure gradients, upward magnetic pressure gradients, which are dominating the support here. But still, there are strong tension forces.
Horizontal average, not volume average.
Sorry. Yes, horizontal average as opposed to a mass-weighted horizontal average. Sorry. Thank you, Axel, for that correction. The reason is obvious. If you have magnetically supported layers, you get this. If only we'd realized this before we'd done the simulation. This is the linear eigenmode of the Parker instability, and I just want to point out that if you look at any particular height, again, black arrows show magnetic field, colors show density. At any particular height, high-density regions are associated with troughs in the magnetic field, that is, upward magnetic tension forces. Low-density regions over here are associated with crests of magnetic field lines, that is, downward tension forces. So you can look for whether Parker is present by just looking at plotting the tension force versus the density divided by the horizontally average density at a particular height. And heavy regions are indeed associated with upward magnetic tension forces. Light regions are associated with downward tension forces. This is clear evidence for Parker. You can see that correlation here, too, in a plot of the magnetic field lines of the simulation. The colors show density divided by the average density. So red regions are anomalously high-density regions. They're sitting in troughs. Blue regions are low-density regions. Those are associated with crests of magnetic field lines. Again, a strong signature of Parker. This is a plot of the fractional horizontal area at every particular height where that Parker-like correlation between tension and density holds. So near the midplane, half the zones are associated with Parker-like tension density correlations, and the other half are not. And the reason is obvious. There is no correlation down there. Your gas and radiation pressure supported, there's no evidence for Parker. But above 2 scale heights on either side, you get this Parker correlation. And if you do a dumb Parker 1966-1967 isothermal linear mode analysis of the Parker instability, it turns out that 2 plus or minus 2H is exactly where you expected Parker to kick in. And indeed, that's where it's kicking in. So it matches. The fact that you're magnetically dominated in those upper layers means that over gas and radiation pressure forces means that those magnetic fields are just tossing this gas around, creating strong shocks. That leads to strong density fluctuations. This is a histogram of the distribution of density fluctuations divided by horizontally average density. At the effective photosphere where the spectrum is actually forming, the solid histogram is at the high energy epoch in the simulation. The dashed histogram is at the lowest energy epoch in the simulation. You have a comparable range of densities, a full width half maximum, which corresponds to 1 dex, but it actually extends over 2 dex in total range. And the dotted curve here shows exactly the same thing for the older gas pressure dominated simulation. So these density fluctuations have nothing to do with compressible magnetorotational turbulence due to the radiation. It's all due to magnetic forces. The upper layers are magnetically dominated here. That has strong spectral consequences. If you have a magnetically supported surface layer, you're going to increase the scale height of the disk, and therefore the densities of the photospheres are going to be lower than you would have expected if you'd have neglected that magnetic support. That means that electron scattering is more important than absorption opacity, which means that the photons are less thermalized with matter than they would be had you neglected that. That means that the spectrum is going to be harder. It's going to be more like a modified black body. Also, you're going to have increased ionization of the photosphere. That's going to reduce absorption edges. That's also going to lead to a hardening of the spectrum. And we've done a radiative transfer calculation through a horizontally averaged version of the simulation, and we verified that. However, the fact that we have these irregular, strong density inhomogeneities acts in the opposite direction. Enhancing the density or pumping the matter causes an enhancement of absorption opacity over scattering opacity, at least in a volume average sense. And that will tend to thermalize the photons, which will soften the spectrum, bringing it back towards a black body. So there are these two counteracting effects in these surface layers, and we don't know what wins. But now that we have a simulation of this, we can do a Monte Carlo run through the 3D structure and see what happens. If any of you are interested in polarization of disks, or electron scattering disks, there's supposed to be this famous Chandrasekhar polarization. I don't believe it's relevant here, because these irregular density inhomogeneities have completely destroyed the plane parallel symmetry, which gave rise to that nice polarization, and the magnetic fields are strong enough to Faraday depolarize the photons at the local effective temperature. So there's no polarization from these disks. So this is a sort of concluding, it's not my last slide, but it just is a summary of the overall vertical structure that we found in this particular simulation. The inner regions, which are radiation and gas pressure dominated, are where the magnetorotational turbulence is occurring. That's where most of the dissipation is occurring, most of the heating. That heat gets out through photon diffusion, not through convection, not through Poynting flux. Because most of the heat is created here, there's almost nothing in the way of a corona above and below the disk. So coronas are not being generated in this particular annulus. The upper regions are magnetically dominated. That leads to Parker instabilities, which creates all sorts of complex weather up there, which will modify the spectrum presumably. So to conclude, these radiation MHD simulations, we now have 3 of them in different regimes of accretion disks around black holes, are handling both the dynamics and the thermodynamics of these accretion disks. So we're now at the early stages of being able to actually make theoretically predicted models of accretion disk spectra. This annulus is thermally stable at this level of radiation pressure. The upper layers are supported by magnetic fields. We don't see photon bubbles in this particular regime with this particular resolution. The Parker instability is instead what's dominating. And we have these 2 counteracting effects on the spectrum, and until we do a Monte Carlo simulation, we don't know what is going to be dominant, and so that's what we're doing right now. We're also trying to understand how photon bubbles work when you have magnetic field gradients. That has never been done before. We are pursuing a new radiation pressure-dominated simulation going back to Neil Turner's original regime. And finally, a caveat, so to be completely honest with you. After having done all this, we were all very nervous about the fact that we have these whopping inward tension forces that are almost, at least in a volume average sense or horizontally average sense, are almost as large as the upward magnetic pressure gradient forces. And so when we did this linear Parker eigenmode analysis, we reached this uncomfortable conclusion. There's a minimum unstable wavelength for the Parker instability, and that minimum unstable wavelength happens to just fit within the azimuthal size of the box. Okay, so this makes me very nervous because the Parker instability develops and those tension forces develop, but the tension cannot relax because you cannot cascade to larger length scales because you're confined by this box. So I'm a little nervous, I'll just be honest with you, about the magnetic dynamics that are going on in those upper layers because the tension is squeezed within this box, and we've just resolved the minimum unstable wavelengths of the Parker instability. So I would certainly like to run a simulation. These are expensive simulations, with a larger azimuthal size to check and see whether this is affecting the results here. So that's a huge caveat that we have here. I'll finish at that point.
Which means there is lots of time for discussion. Yes, please.
So you are using outflow boundary conditions.
Yes.
So you have a magnetic buoyancy.
Yes.
So you are losing matter. Then how
We lose almost no matter through the course of the simulation, actually. It heats up, it cools down, it heats up, but very little mass loss occurs at the upper boundaries. The overall mass in the box at the beginning and the end of the simulation, it's basically the same. We've lost very little mass, yeah. And that's because we've gone up to 8 scale heights on either side of the mid-plane. That's what those 512 zones were for.
Yes.
Yes, I was just wondering, do you place your box also closer to the black hole or farther away?
No, so Neil Turner in his original simulation did place it closer to the black hole, and that was where the radiation pressure was dominant. But with the code that he had at the time, which was not parallelized, he could not include the photosphere within the domain of the simulation. It's not clear that that matters, but we still don't really know what happens in that regime. He did not find any evidence for thermal instability, but I think he would be reluctant to claim that that's strong evidence that there is no thermal instability. We simply don't know. Yeah, but Neil can address that himself. Mitch was the person that raised his hand, by the way.
I'm chairperson. I saw this person raise his hand first.
Okay.
Go about it.
The radiation pressure-dominated disks were alpha disks, that is, were also supposed to be viscously unstable.
Yeah.
And that is something which is typically illustrated in terms of these S curves.
Yeah.
So, but the abscissa on the S curve is the average density.
Yeah.
So that is conserved in your simulation.
Yes, that's right. It's necessarily conserved it's not conserved because you could have outflows. There are no significant outflows here, but in the geometry of the shearing box, there is no net accretion because it's a Cartesian box basically with Coriolis forces acting. So even though we're getting all of this accretion power liberated, there's no gravitational energy loss. There's no net mass accretion, and you cannot change the surface density in that way. It's because it's shearing.
Can be answered on the question.
Yeah. So we can't address the viscous instability, in other words.
Can you tell whether the magnetically dominated zone is closer to an exponential or Gaussian structure, or is it closer to a parallel vector?
We plotted the curves, but we have not tried fitting them. I don't know the answer to that question. You have ideas as to what it should be.
I've tried plotting them also, and I can't tell.
Okay. I have not tried doing that.
Yes, go ahead.
Actually, I just have a simple set of questions. So, presumably this is an NPI simulation. How did you tile the computational domain?
That's a question for Shigenova Hirose. I have no idea. I am the ignorant analytical guy who can take data from a simulation, but I have no those sorts of questions. I have no idea.
How long did the simulation? Do you know how long it ran?
I know how long it ran in human time. I don't know how long it ran in computer time, which is really what you're asking. It ran for many months of human time.
Okay.
I have 4. Ed, Harold, Paul, Augie, in that order. Ed, please.
This rash of corona sort of surprised me enormously, so could you elaborate on why we don't have
Can you repeat the question, please?
Anticipation going on, instability slowing.
So Ed is asking if I could elaborate on why there is not a strong corona there. I mean, there is a corona in the sense that there's a magnetically dominated surface layers, that there is heating going on up there, mostly through shocks, but that's a negligible fraction of the total accretion power that's being liberated in the annulus. Most of that accretion power is being liberated at the midplane. Why that is, and why it disagrees with, clearly, observationally, in black hole systems, you see hard X-rays. That could be because those hard X-rays are not originating from a locally generated corona. They have to do with the global structure of the flow. It could also be that because we haven't gone into the radiation pressure dominated regime, magnetic buoyancy might be altered, and maybe there's a way of getting the accretion power out and dissipating it mostly in the surface layers. We don't know.
Clarification, actually.
Is it a comment on this point?
Is it really true that the maximum dissipation is at z equals 0, not at z equals plus minus h? Which
it's at z equals 0.
But this is not what I saw in the plot, I thought.
That's because I didn't plot md. So the dissipation rate per unit mass scales as m to the minus 1/2.
Okay, right.
If I multiply by m, it's where the maximum.
But you want maybe per volume, the heating per volume. That would of course peak then.
Yes, that's a different question, right?
Harold.
So your disk went through hot and cold phase.
Yes. Yeah.
It seems periodic, but I guess you only had like one.
But it begs the question though. There's a characteristic time scale where it looks like that.
Yeah.
And that's many thermal times. The thermal time here is 7 orbits. And those things were about 100 orbits in length.
So what sets that?
I have no idea. It has to do with the turbulence, and I don't know. It's the heating side of the equation. It's not the cooling side, clearly, because the thermal time is way too short. We do not know. That's one of the most interesting questions that we haven't been able to answer. I'm sorry?
How many of them do you see?
Well, it goes up, and then it goes a little ways up again, and then it goes up again. Well, I would be reluctant to call that a period. There seems to be some sort of time scale there, which we do not
Short
know.
of time. Paul, please.
Just to follow it, Spiegel's comment up a little bit. The Park instability always implied that while the dense regions were falling,
Yes.
there were magnetically buoyant regions
Yeah.
that were rising.
Right.
And so I would have thought that you couldn't have one without the other, and there is your corona. So,
Right. So
what do
here.
you mean if you don't? Do you not self-consistently
Well,
see the
okay.
generation?
When I say that there's no corona, I mean that there's no energetically significant corona. That is, most of the accretion power is liberated at the midplane. The sun has a corona in the same sense as I'm saying. This disk has a corona in the same sense as the sun. Most of the luminosity of the sun is not coming from dissipation of magnetic fields in the corona. It's coming from nuclear reactions in the core. The same thing is happening here. So there is still a corona in that sense. There are magnetic fields up there. They are dissipating, but it's a negligible fraction of the total accretion power. Now, why that is unclear. It may be due to the finite size of the box, where I build up tension, so those buoyant magnetic fields rise, but then there's enough tension force that they stop rising, and that saturates the instability. That could be the problem here. We don't know.
The other thing is that what makes them hot in the sun, these magnetic arches, may be something, a physical process you don't have in your...
Absolutely, and I certainly don't claim that we're modeling a real kinetic reconnection in the simulation.
Okay,
or
and then
microflares or anything like that. That's right.
okay, and then Jürgen.
Could you possibly back up to the slide that shows the fluctuating dissipation, the scatter plot with the dissipation?
Yes.
So what this showed was a correlation between dissipation and energy, a linear thing that turned over into possibly some saturation.
Yes.
There's a chicken and egg problem here. You have it there.
Yeah, sorry, I overshot.
It's a situation where you have a quasi-static energy equilibrium. So if you have some cooling proportional to temperature, this is exactly what you expect. It's the passive response of pointwise heating is precisely this response. If you have a cooling proportional to energy, So I'm just seeing that.
Yes, if you have a balance between dissipation and cooling, and cooling is proportional to the energy, which it is here, it's clear, then yes, you would have that linear response. It's more that the dissipation rate is scaling with... Let me back up. You're right that because we've gone over so many thermal times, you have a balance between dissipation and cooling. So maybe this is saying, this is the instantaneous volume integrated dissipation rate. But yeah, this part of the curve is perhaps just showing that you have a balance between dissipation and cooling, especially given all the scatter. The instantaneous dissipation rate is doing all sorts of things. So maybe this result is somewhat trivial. This turnover is not so trivial in that sense. But it's not, you judge whether that's real or not. It might be, we're speculating that this might be why it's stable, but you can see that it's a conclusion of somewhat dubious, the evidence is somewhat dubious here.
Jürgen, please.
Yeah, you have pointed out that both for the MRI and also the bubble, the propagation of wave modes is important. And if you would look back to the original paper by Stone and Norman describing the ZS code, because of the underlying HD code, you can easily follow the HD mode, and also you can follow the characteristics of the alpine mode. But there were doubts that you can actually follow mixed modes. Has this changed?
Such as fast and slow magnetosonic modes, you mean? I see. The only evidence I can, with which I can address that, the MRI it's not. It doesn't really deal with propagation of modes. The photon bubbles, which are overstable modes, they are traveling waves which are amplifying. That is a concern there. And the only thing that I can say there is Neil Turner did simulations in 2005, which carefully looked at the growth of photon bubbles with this same code, and his simulations matched the analytically predicted growth rates spot on. So I think that's not an issue here, but that's just the linear growth phase. And I should also say that his shotguns that developed also matched Mitch's analytic solution. So I think that's okay.
Well, after having just set the record for questions answered, let us thank the speaker again.
Announcement, our secretary Anita gave me some forms. They are in Swedish, and there is a brief explanation on the first page. So people who expect reimbursement need to fill in this form and return it per annum. There's another thing. Yesterday there were 2 people who didn't get 5 krona money back when paying for the lunch or something like this. Anybody here?
Yeah.
And so here are these forms. I think that maybe on this chair here. So please everybody take
Yeah. I didn't address the sign of the differential rotation. Yeah.
I think that the beautiful cartoon,
Yeah.
that shows
This extra step needs to be fixed, I agree. The cartoon is incomplete in that sense, yeah. Yeah, I've been thinking about that for a while, but I haven't figured out a way of explaining that.
well, I remember another cartoon from the
Yeah.
which are a little bit more elaborate, but they are figuring this out, that it is necessarily non-constant.
Yeah. Well, yeah, if you can talk about springs, and there's an exact, you can build it, but I didn't have time. There's no way.
Sure.
There's no time.
It was so much time, but wow, it was interesting.
Oh, thanks.
Yeah, and then, one, sorry. You can mention that most of the heating then comes in the mid-plane, right? Yeah. But
Yeah,
then,
that's right.
Yeah. But then the mid-plane then might be neutral, right?
Might be in the...
neutral.
Oh, neutral.
Yeah.
Sorry, right. So this is all... Yeah. No, that's a very good question. So, yeah, this is all fully conducting. So we're not talking about the interstellar regime at all. That's an interesting question. What would happen if MRI is happening mainly in the surface setting? Yeah.
The whole thermal will change, right?
Yeah, I agree. I totally agree. So none of what I've said here I think applies to protostellar disks. That's a completely different ballgame for the reason that you said.
Yeah, it's an interesting issue then, because can the Taurian disk then we then have the illumination, right?
Yes.
Yeah.
Right.
Yeah, which is the biggest heat source.
Right. It's a passive disk basically. Yeah, that's right. Yeah.
So then, it would then change totally, right?
I agree.
Yes,
so that's the second reason why they're very different. I totally agree. Yeah.
And then, can the black holes then the disk can be
flared, and you can also get reprocessing of interdisk radiation. Yes, so you can get surface heating. That's true. In the outermost, at large radii, that can be a significant effect, and that's an effect that we have not looked at here. It's all what's happening internally. So yeah,
that's interesting.
There are all these extra things that we have not addressed. Yeah.
Right.
Yeah.
Okay.
Yeah, but those are all extremely good ideas that someone needs to explore.
Yeah. In a global disk, how many grid cells can you think that would be needed? Because
To resolve a lot.
like 500 cells, can blow this. That's
You can't do. Yeah, you can't do that. That's why these sorts of simulations can't be done globally. It's pretty depressing because there's some aspects of the physics that rely on the global structure, and we can't access that with current computer algorithms at least. Maybe these other algorithms can improve on this, but you still need that high spatial resolution.
That's true. Like I am coding that with 128, like in Z, right?
Yeah.
We can in 64 processors, and it takes like 15 days to code. It's a long time. We can with the 500 points, so it could be months. So that's just too much time.
It's depressing. So I have these high hopes of actually building accretionist models that are fully consistent, but you're right, but until we have global simulations, we're still going to be in the dark on major issues. So maybe 20 years from now,
maybe so, but now we could see the major things made. Like you mentioned that the heating rate actually happens in the grid is okay, right?
The grid is
no.
What
like in the grid dissipation.
Yes, the heating rate is almost entirely due to grid dissipation. That's right.
So then, you see more heating, if you have less points then for.
Oh, we haven't even done that. We haven't even done coarser resolution studies.
Really?
Yeah, but then you're right. That's something that's fairly straightforward to do. But we have not tried that. Yeah, not even that. It took months to do that, and then we've been analyzing the data. But now that we understand it, there's a lot more work that needs to be done on just coursing the grid to see how that matters, widening the box, see how that matters. And none of that has been done yet. Those are fair questions, and that it needs to be done.
All right.
Thank you though for that. I need that critique. So, did I set you up properly though? Okay. Yes. Oh. Okay. And they matched exactly what you said. So what is he referring to with stone and bone, where he was having the mixed modes don't calculate angle pi? So that's all with chemical radiation and diffusion, things like that, right? But not just a simple propagation of the solar magnetic sun, for example.
Thanks very much for sharing this session.
Thank you. Everybody was so well behaved.
Yes, that's true. Yes.
Oh,
I forgot to.
Okay.